SwayamPrabha. Digital India. Educated India.
I welcome you all to this session. In this session today, we shall solve one or two numerical problems. Those are related to steam power cycle. So, you know that if we try to recall, in this module of this course, we have discussed about steam power cycles, I mean different cycles starting from the Carnot cycle to the binary fluid cycles. Now, we have seen that efficiency of the Carnot cycle is the maximum, that is what you have read even in your thermodynamics course, but you know identifying a few issues in from the perspective of operation as well as design, there are a few practical cycles, we have also discussed them. So, we have discussed about that efficiency of the Carnot cycle is maximum, but if we talk about simple ideal Rankine cycle, reheat Rankine cycle and also then regenerative cycles, just starting from the simple ideal Rankine cycle, several other modifications that we have discussed are essentially for the improvement of the thermal efficiency of the cycle. So, till now we have discussed about this particular aspect, that is thermal efficiency from a qualitative perspective, that is you know that Carnot efficiency is maximum 100%, while efficiency of the you know ideal Rankine cycle or Rankine cycle with reheating efficiency reduces. So, to have a quantification of the thermal efficiency in a steam power plant, we need to solve a few problems. So, accounting for this aspect, today we shall solve two different problems. One problem I have taken from the simple ideal Rankine cycle. This problem we shall illustrate here only to have you know fair idea about the solution of a problem. So, let us first read out the problem statement. A simple ideal Rankine cycle with water as the working fluid operates between the specified pressure limits. The rate of heat addition and rejection and the thermal efficiency of the cycle are to be determined. Given that boiler pressure is 6 megapascal, condenser pressure is 20 kilopascal and steam temperature at the exit of the boiler is given 500 degree Celsius. So, from this input data we need to calculate the heat addition, heat rejection and thermal efficiency. In fact, if we can calculate the amount of heat which is rejected to the you know cycle and the amount of heat which is added to the cycle or rejected from the cycle, knowing these two parameters we can quantify the efficiency. So, if we try to solve this problem, you know that I will discuss today, though it is a very simple problem, but I have taken only to make you understand that there are a few steps. So, whenever you are solving any numerical problem on this particular topic, the first objective should be to draw the schematic depiction of the steam power cycle. So, let us do it. we have boiler, then turbine, and after doing work steam is taken to the condenser. From there collected steam is pumped back to the boiler. So, this is 1, this is 2, this is 3 and this is 4. Basically, we have tried to, so this is the, this is pump wherein work is added, this is condenser. So, this is Q out, this is W out, this is Q in. So, this is the schematic depiction we have discussed so many times. So, now it is given that the cycle is operating between two specified pressure limits. So, then what we need to do? We need to write down the quantities which are given in the problem statement. So, boiler pressure, so before going to write them, let us draw the TS diagram. So, if we try to draw the TS diagram, so you know that we have learned it, TS diagram, this is constant pressure line. So, this is P condenser. P condenser and this is P boiler. So, that is the most simple cycle, just the modification of the Carnot cycle, because in Carnot cycle we have seen that there are issues like partial condensation, and finally handling such two phase mixture pump cannot be used. So, compressor is used, and while we are using compressor and that too it is two phase mixture, it is because of the higher specific volume of the steam, power consumption needed, power consumption by the compressor is a substantial part of the work output. So, that is why it is not a real cycle. So, here if we try to recall, nothing is mentioned about whether steam is reheated or not, steam is superheated or not. So, you know that steam temperature at exit of the boiler is given 500 degree Celsius temperature. Perhaps this is the line which is giving us a clue about the quality of steam at the exit of the boiler or at the inlet to the turbine. So, let us complete it first. So, this is the point 1, this is point 2, this is point 2, and then we do not know whether point 3 will be on the saturated vapor line or it will be in the superheated regime. So, what we need to do as of now, what we know? We know given quantities are, boiler pressure is given 6 megapascal. So, P2 will be equal to P3 equal to 6 megapascal, okay. Because we could not map the point 3 on this TS plane till now, we are waiting to understand whether 3 would be on the saturated vapor line or it will be in the superheated regime along this line. Whether it is on the superheated saturated vapor line or it will be in the superheated regime, it will lie on this vapor pressure line. So, this is P 2 equal to P 3 equal to 6 megapascal, condenser pressure is 20 kilopascal, that is P 1 equal to P 4 will be equal to 20 kilopascal. Since we could not locate point 3 on the T s plane, we also could not locate point 4, right, because 3 to 4 is the isentropic process that is occurring inside the turbine. So, next is T 3 is given, that is 500 degrees Celsius. So, these data are given because temperature at the exit of the boiler is 500 degrees Celsius temperature. So, now which is most important to understand at this point of time is where the point 3 is, whether it is on the whether it will be on the saturated vapor line or it would be in the superheated regime. No matter whether it is on the saturated vapor line or superheated regime, it will lie on the special line, that is the boiler pressure. So, to understand that, let us quickly look at the steam table, right. You have learned to read data from steam table in your thermodynamics course, but I am not going to discuss all those part. But what we can do, that if we can, since this is the exit temperature of the steam at the boiler, so that is the inlet temperature, inlet condition of steam, condition of steam at the inlet to the turbine. So, if we can, we know the temperature and the point 3 will be on this special line. So, we know also pressure. So, P 3 is also 6 megapascal, that is what I have already written. We know T 3. So, now we can look at we can read this point, whether the point will be in the superheated regime or the saturated vapor line by looking at the steam table. So, let us quickly look at the steam table. So, if we go to look at the steam table, so we have seen that pressure is 6 megapascal and temperature is 500 degrees Celsius. So, we shall go to first saturated water pressure table, not the temperature table, because pressure is mentioned. So, if we know, if we look at the saturated water pressure table and if we can find out that corresponding to that pressure, that is 6 megapascal, what is the saturation temperature? If the temperature, saturation temperature is less than 500 degrees Celsius temperature, then definitely point 3 will be in the superheated regime, or if the temperature what is given 500 degrees Celsius, if it is equal to the saturation temperature at that pressure, then it would be on the saturated vapor line. So, let us look at the saturated water pressure table, but the given temperature is 500. So, it is well above than the saturation temperature. So, definitely point 3 will be in the superheated regime. So, now if we go to the slide, then we can locate point 3 in the. So, that means point 3 will be in the superheated regime. So, here this is point 3. So, this is point 3 and this is point 4, right. So, point 3, state point 3 is in the superheated regime. Next, we have to identifying the location of point 3 in this T s plane. Next, what we need to do? We need to apply just steady flow energy equation that we have seen, that we have discussed across all the components. So, basically if we apply steady flow energy equation to the boiler, steady flow energy equation to the turbine and steady flow energy equation for the process which is there in the condenser, as well as steady flow energy equation to the process which is there in the pump, then we can find out what would be the work and heat interaction, right. Essentially, if we need to quantify the efficiency as well as the amount of heat which is added or rejected to the cycle. So, we need to quantify, we need to apply the steady flow energy equation two different components, and knowing fully that boiler is a heat interacting device. So, we can calculate what is the amount of heat being added to the boiler. The amount of heat which is added to the boiler. Turbine is a work interacting device. So, basically by applying the steady flow energy equation we can quantify the work output from the turbine. Similarly, condenser is again a heat interacting device, because I think there is no work output from the condenser. So, what we can do, we can calculate this quantity, that is Q out, and finally the amount of work which is added to the pump also can be calculated by applying steady flow energy equation to the process which is there in the pump. And I am not going to discuss, because already you have discussed, we have quantified and you have also established the mathematical form. So, straight away what we can do, we can start solving this problem. So, we will assume that this is the kind of understanding you should have before you go to solve a particular problem. That since it is a pump and which cannot handle two phase mixture, essentially the quality of thermodynamic state of the liquid, thermodynamic state of the working substance at point 1 should be the liquid. So, it is the saturated liquid. We know the pressure. So, if we go, so basically H1 would be equal to Hf corresponding to 20 kilopascal, and P1 will be equal to P4 equal to 20 kilopascal. What we need to know? What we need to know also, that is V1, that is specific volume, that is Vf corresponding to 20 kilopascal. So, all these are needed. Again H1 equal to Hf at 20 kilopascal, that is specific volume of the specific enthalpy of the liquid corresponding to the pressure 20 kilopascal. Again we need to look at the steam table, then we can solve, we can find out. So, that if we go to the steam table, then again we have to go to saturated water temperature table, because saturated water pressure table. So, pressure is 20 kilopascal. Now, we can see 20 kilopascal, Vf is 0.001017. So, if we go to this particular row, that is 20 kilopascal, Vf is equal to this, and similarly we also can get Hf from this enthalpy table. So, enthalpy would be 251.42 and specific volume of the liquid will be 0.001017. So, now again we can go back to the slide. So, we can write that H1 I am writing directly. So, H1 will be equal to 251.42 kilojoule per kg, and V1 is equal to 0.001017 meter cube per kg. So, that is what we have calculated. Now, so what would be W pump? So, W pump, that is nothing but V f at 20 kilopascal into P2 minus P1. So, you can understand, in fact, I had taken enough time, because maybe to discuss a particular aspect I had taken time which is even beyond the normal time which I was supposed to take, but I had taken it only to make you understand, only to discuss the things more carefully. So, now we had discussed that work added to the pump is nothing but it is not PdV, rather it is VdP. So, whether the process is a reversible isothermal process or reversible adiabatic process, work done is always VdP, that is what we had established in one of the previous classes. So, what is VdP? So, this is the volume of liquid corresponding to pressure, that is the condenser pressure, and So, this is the change in pressure. In fact, the pump is responsible to build up this amount of pressure. So, this quantity would be equal to, you can understand. So, this quantity will be equal to 0.001017 into 6 megapascal. So, 6 minus 20. So, if you calculate it, you will get it 6.08 kilojoule per kg. So, this is basically the amount of work that is added. So, work added to the pump. Okay. We had written small Wp because it is specific work, because we are trying to express quantities per unit mass per kg of the working substance. So, that is 6.08 kilojoule per kg, fine. Now, so basically if we go back to the previous slide, we know enthalpy at state point 1, and then finally we had find out the work done needed to complete the process 1 to 2, right. What we need to know? We go to the next stage, that is the boiling. So, the amount of heat required to be added to the boiler for conversion of water into steam is nothing but change in enthalpy, and that is what we could write from the from the application of steady flow energy equation to the process which is there in the boiler. So, you know, I can straightway write that small q in. Okay, so, if I go to the, so this is process 1 to 2, and finally I will go to process 2 to 3. So, that is q in equal to H3 minus H2. So, this is specific heat added, because again I am trying to express the quantity in terms of, I mean in the specific form. So, per unit you know kg of the working substance, per kg of the working substance. So, this is q in, small q in. So, this is q in. Now, H3 you can calculate, right, because you know, try to understand H3 you can calculate because you know pressure, you know temperature. So, again I am just trying to recall whatever we have learned from our thermodynamics course, that is two independent intensive properties are required to specify the state, right, state postulate that you have studied. So, you try to understand, once we know temperature and pressure, then perhaps we can calculate other properties, but since it is a pure substance we cannot apply the, had it been an ideal gas, we could have applied the ideal gas equation to calculate other properties, but since it is working substance we need to consult steam table. So, by looking at the steam table, to be precise superheated water table, we can calculate other properties like enthalpy, entropy, internal energy, etc. So, what we can do? We can calculate H3 from the superheated table, but we also need to calculate H2. By how we can calculate H2? Look at the process. So, you know enthalpy at state point 1, right. We also have calculated work done, work which is added to the pump. So, again if you apply steady flow energy equation, you can see enthalpy H2 would be equal to H1 plus the amount of work which is added to the system, that is in the pump. So, what we can do? We can write first that H2 equal to H1 plus W pump. So, H1 already we know that is 251.42 kilojoule per kg. So, this is 251.42 plus the pump which is used here consuming this amount of energy for its operation. So, this is 6.08. So, total if you calculate it will be 257.50 kilojoule per kg, which is very important because you always need to write unit, otherwise you may come up with wrong answer. So, this is the H2. So, we have calculated H2 just by applying the steady flow energy equation to a process which is there in the palm, and then we need to, so H2 we have calculated, H2. So, we need to know what is H3. So, already we had we have discussed that at that pressure, since point 3 is lying in the superheated regime. So, we have to go to the superheated table to calculate the enthalpy, knowing the pressure and temperature at that point. So, if we go to the next slide, so we can go here. So, P 3 equal to 6 megapascal, T 3 equal to 500 degree Celsius. So, from the superheated table, we can calculate H 3. So, let us I am just for this problem trying to consult steam table repeatedly, because only to make you understand by how we can read data from the steam table. So, again if we go to the steam table, where we should go? We should go to the superheated table. So, we know pressure and temperature. So, this is the saturated water pressure table. So, we have to go to the superheated table. So, this is A6. So, this is superheated water table. Now, as I told you, this is superheated water, but temperature is given at the extreme left column, but either we can look at the temperature, from there we can calculate other properties, but this is pressure is given, P is equal to 0.01 megapascal. So, P is given 6 megapascal. So, 6 megapascal, that is this table. So, this is the table that is top left corner, and what we can see 6 megapascal, and then that temperature is given 500 degree Celsius. So, this is 500 degree Celsius temperature, pressure is given. Now, all these are the several properties. So, basically we need to know enthalpy, starting from the first one, that is specific volume, then internal energy, and third column is the enthalpy, and fourth column is the entropy. So, what we can calculate? We can calculate both enthalpy and entropy. So, for this 600 megapascal corresponding to this temperature 500 degree Celsius temperature, enthalpy is 3423.1 kilojoule per kg and entropy is 6.8826 kilojoule per kg Kelvin. So, we can go to, because entropy is also required. Why it is required, I shall explain immediately next to this task. So, I am now going to the slide. So, what we can calculate? Enthalpy, that is 3423.1 kilojoule per kg, and S3, that is specific entropy, is also 6.8826. This is kilojoule per kg Kelvin. So, this we had obtained from the steam table. So, once we have calculated H3, we can calculate small q in, that is equal to 3423.1 minus H2. H2 is 256.50. So, this is 257.50. So, 257.50, and that is coming as so this is q in. So, you can calculate what would be the q in. Okay. Now, what we can do, we can calculate what would be the Q out. So, this is the amount of heat added to the boiler. So, this is the first part of this problem. If we go back to the problem statement, you know the rate of heat addition. So, this is the this is the total amount of heat added to the boiler, but you can understand if we know the mass flow rate of the working substance. So, if we multiply this quantity with that m dot, then we can calculate what is the rate at which heat is added to the cycle. Okay. So, this is what is the heat addition. Now, last another part is because see we also need to calculate heat rejection, that you can see that would be in the condenser, and finally, if we can calculate the amount of heat rejected, from there we can quantify the thermal efficiency. Okay. So, what we can do now, we can go to the next process. So, this is process. So, this is process 3 to 4. So, this is isentropic expansion. Isentropic expansion, what you can see, because few minutes back I told that we need to calculate entropy as well. So, we had calculated entropy corresponding to that particular state point 3. Why it is? Because if we know the entropy at state point 3, and that would be entropy of state point 4. Why? Let us look at the TS diagram. So, you know this is isentropic process 3 to 4. So, if we know the entropy at state point 3, then entropy at 4 will be equal to entropy at 3. So, that is S 3 equal to S 4. Now, why? Because again I am telling state postulate, you need to know two intensive independent properties to calculate other properties. So, you understand very well that till now we have calculated work done, work added to the pump, heat added to the boiler. Finally, we need to calculate the turbine work output. So, if we apply the steady flow energy equation to the process that is occurring inside the turbine, the work interaction between system and surrounding will come out, or can be written in terms of the enthalpy drop. So, basically you know that work out would be equal to S 3 minus H 4. Somehow we have calculated H 3, but we have to calculate H 4, right. So, if we need to calculate H 4, then if we focus at this particular point on the TS plane, we know only pressure, because the point 4 is lying on this condenser pressure line, and only by knowing one property we cannot calculate other properties from the steam table. What we need to do? We need to calculate, we need to know at least another one intensive property. So, now knowing the process is isentropic and we have measured the entropy at state point 3. So, we can write S 4 will be equal to S 3 and P 4 is known. So, you can understand that S 4 equal to S 3 equal to 6.8826 kg kilojoule per kg Kelvin, and P 4 equal to 20 kilopascal. So, these two properties are good enough to find out the enthalpy at state point 4. By how? Again this is something we need to understand. See, if we go to the TS diagram, the state point 4 is inside the vapor dome. So, that is, I mean quality of point 4 is neither pure liquid nor pure vapor, right. So, it is a two phase mixture. So, the point 4 is not lying on the saturated vapor line, nor it is lying on the saturated liquid line, rather it is inside the vapor dome. So, it is a two phase mixture. So, you know that again you have studied in thermodynamics, we know pressure, we know entropy at state point 4. By knowing this, we need to calculate what would be enthalpy. So, what we can do very quickly, you know that this H, total H is equal to H f plus x 4 into H f g, right. So, if we try to calculate enthalpy at state point 4, then we need to calculate enthalpy at 20 kilopascal plus x4 into HFG at 20 kilopascal. So, that we will get from stream table, provided we know this fellow, that is the quality. So, this is quality of the mixture. Had it been pure stream, it would have been 1, quality would have been 1, but it is not the pure stream because the point is not lying on the saturated vapor line. So, what we can do? We need to first calculate H4, because HF corresponding to 20 kilopascal you can get it from stream table, HFG corresponding to 20 kilopascal you will get it from stream table, but if we need to calculate H4, then what is essential to know is X4. By how we can calculate? So, now you know it is very important that we know entropy. So, somehow we have calculated S4, that is 6.8826, 6.8826 equal to SF at 20 kilopascal plus X4 SFG at 20 kilopascal, SFG plus 20 kilopascal. Right, into X4. So, now we know this. So, basically X4 will be equal to 6.8826 minus SF at 20 kilopascal divided by SFG at 20 kilopascal. Can't we calculate entropy of liquid, saturated liquid, and SFG corresponding to 20 kilopascal from stream table? We can. So, let us again go back to the stream table and we can see. So, 20 kilopascal we have to go to the saturated water pressure table. So, saturated water pressure table, this is, and it is 20 kilopascal. So, this is the case. Now, you can see this is 20 kilopascal, right. So, you can see that 20 kilopascal, it is clearly written what would be HF, what would be HFG, what is SF, what is SFG. So, you know that 20 kilopascal. So, if we traverse along this horizontal line, we can write HF, that is 251.42, already you have calculated, HFG is 2357.5, SF is 0.8320 and SFG is 7.0752. Check it, because you know that SG is 7.90, but the entropy at state point 4 is less than SG. So, it indicates that it is not on the saturated vapor line and it is in the two phase zone. So, we know the 0.8320 is the SF, 7.0752 is SFG and 2357.5 is HFG, 251.42 is HF. So, knowing this, we can again go back to the slide and we can calculate the enthalpy at state point 4. So, if we write it, so this is 6.8826 minus what I told 0.8320 divided by this is 7.0752 and it is coming, X4 is coming 0.8552. So, you can understand. So, this is 85%, right. So, 85% is steam, remaining almost 15% is water. So, this is two phase mixture. So, now if we plug in the value of that over here, so this is 251.42 plus 0.8552, that X4 we have calculated from here, and HFG, that is 2357.5, right. So, if we calculate it and it is coming as 2267.5 kilojoule per kg. So, this H4, this X4 we have taken from this. Okay. So, we have calculated H4. Once we have calculated H4, now we can calculate the work done. So, this is work W out from the turbine, that is H3 minus H4. You may ask me why it is not H4 minus H3, because it is because of this enthalpy drop we are getting work output. So, enthalpy will drop in the course of flow of steam through the turbine, and it is because of this reason we will be getting work output. Essentially thermal energy will be converted to the mechanical energy in terms of work. So, heat that is added to the steam, that would be converted into work in the turbine. So, now we have calculated H3, we have also calculated H4. So, H3 we know because H3 is the that already we have calculated 6 megapascal 500 degree Celsius. So, so H3 would be equal to, from the let us write here that 3423.1 kilojoule per kg. So, this is from the superheated table. So, this is from the superheated table. Because we know pressure and temperature. So, P4. So, this is already H3 already we have calculated. So, now what we can do, we can calculate process 421. So, W out, that is H3, that is nothing but 3423.1 minus H4, H4 is 2267.5. So, 2267.5. So, this is the amount of, work done. So, right. So, this is work done. So, this is work done by the steam. So, this is rather I can write work output from the turbine, work done by the steam on the rotating part of the wheel. So, this is work output from the turbine. And finally, process 421, that is constant pressure heat rejection. So, constant pressure heat rejection, that if we look at the TS diagram. So, this is 421, we have calculated H4, we also know H1, because H4 we have calculated by this linear interpolation, and H1 already we know because it is HF corresponding to that pressure 20 kilopascal. So, H4 is this quantity and H1 that is this quantity. So, this is basically H1. So, what we can do, we can quickly calculate Q out, that is H4 minus H1, and that is nothing but 2267.5 minus 251.42. So, this is kilojoule per kg. So, this is second part of this problem, that is amount of heat rejected from the cycle, right. So, this is another answer of this problem. Again I am telling, if you would like to calculate rate at which heat is rejected, we need to know the mass flow rate of working substance, and then we can. So, if you multiply this quantity with m dot, then that would be kilojoule per second. In fact, if you multiply by kg per second. So, try to understand that if we try to multiply with m dot, that is kg per second, then perhaps it will be getting kilojoule per second. So, kilowatt, in fact joule per second watt. So, basically kilowatt, that is the rate at which heat must be rejected. So, we need to know, because we are everything we have calculated per unit per unit kg of working substance, whether it is steam and steam water. So, this is basically we have calculated. Now, finally, which is very important, that is thermal efficiency. So, thermal efficiency, eta thermal, if we assume that all the processes are internally reversible, right. So, that is nothing but 1 minus q out by q in. You can check, and if you plug in the value, answer will be 0.363. So, that is 36.3%, right. So, try to understand, efficiency is very poor, right. Also, by looking at this expression H q out, so you can understand the amount of heat that must be rejected in the condenser, because we could not consume the enthalpy in the turbine. So, you can W out, you see enthalpy at the inlet to the turbine is 3.4 to 3.1, and enthalpy of steam at the exit of the turbine is 2 to 67.5. So, a substantial part of enthalpy is going out from the turbine without doing any work, and it is because of this reason thermal efficiency of the cycle is only 36.3%. Before I go to complete for this session, I would like to complete this session. I would like to tell you, that you also can check whether efficiency is coming as 36.3% or not. By how? You can W out, Q in. So, basically you can see whether you can calculate efficiency W out by Q in, and you can check whether the efficiency is getting equal with this or not. So, you know that while you are calculating W out, so basically you have to calculate W net. So, you know that we are also giving this much amount of work input to the cycle. So, this much amount of work must be subtracted from the turbine work output, and that is the net work output, right. So, if you would like to calculate efficiency, then this much amount of work must be subtracted from the W out, and that work should be divided by the heat input, and that is the thermal efficiency of the cycle. So, to summarize, what we did today, we have by illustrating this very simple example, we have seen the steps, the procedures by which, rather we have discussed methodically all the steps which are involved to solve this type of problem. I would suggest you, before going to solve this type of problem, what you need to do, you need to first draw the schematic diagram, and then it would be convenient for you all to solve the problem if you can map all the processes in T S plane, and afterward only just by you have to apply steady flow energy equation, and you have to consult with the steam table. So, with this I stop here today.